This next example is a little bit more complicated. Now, I've tried to help by leaving this as 2 divided by 2 instead of just 1, but keep in mind that if this was a 1, we could change this to whatever is still equivalent to 1 that will help us identify what the pattern is. Now, just like we did in the last example where we identified the odd terms and the fact that it changes from positive to negative separately, I'm going to look at the top and the bottom separately. So you'll notice on top, it actually just changes by a single term every single time. So that means that on top of this summation, I'm going to have I equals from something to something. I'm going to want to start at I on top. Now, if I do that, that means that I'm going to actually start at 2. And if I start at 2, I'm going to have 2, 3, 4, 5, 6, and the last term I'm going to plug in is 7. So if I do it this way, I should start at 2 and end at 7. Again, there's other ways to do this example, but I would argue that this is the most efficient way to start it, to look at it. Now on the bottom, you'll notice we start at 2, we go to 5. From 5, we go to 8. Notice these are not just odd, these are not just evens. But what do I do from one term to the next? Notice I'm simply adding 3 every single time. So what that means is that if I'm adding 3 every single time, it should be some form of 3 times the indexing variable plus wherever I happen to start. Again, if I plug in 1, now this might be, again, slightly tricky because of the way we've set this up in terms of the I, but if I plug in 1 here, that means I get 3 times 1 plus 2, which gives me 5. If I plug in 2 here, you notice I get 3 times 2, which is 6, plus 2, which is 8. So it does cycle the numbers correctly. If I plug in 4 and so on and so forth, I'm going to get the correct values. The problem is that I'm starting at 2 here, which means that I've got to back cycle this example so that I'm starting somewhere else. Well, there is a nice, consistent way to do this. There is something we called an arithmetic or an arithmetic sequence back in algebra. A sub n is equal to the starting term plus your common difference times n minus 1. This is the formula that will actually represent this pattern, 2, 5, 8, 11, 14, 17, because we're adding the same number every time. Or d, the common difference, is the number that you're adding every time. A sub 1 is the term you're starting with. That's your 2 value down at the bottom here. And then n minus 1 is simply just the indexing value we're going to work with. So a sub n I'm going to refer to as 2. Actually, I'm going to change that to an I. I prefer that as an I. 2 plus 3 times I minus 1. And you'll notice in this case, if I rearrange it, it's 3 times I minus 1 plus 2, which is actually very, very similar to this, is it not? You'll notice then that this becomes 3i minus 3 plus 2, which is 3i minus 1. Now, if I go to plug in 2, do I get back 2? And you'll notice 3 times 2 is 6, minus 1 is 5. So I'm still a term behind, which means that I should definitely go ahead and manipulate this by one step further. Again, if I'm still one step behind, let me go ahead and you'll notice I went from here to here. I subtracted 3. Let me subtract 3 one more time. 3i minus 4. Again, some of this work ends up being kind of like a guess and check. Some of it's representing a pattern. But the pattern is that I'm adding 3 or subtracting 3 every single time as I move forward or backwards. Now if I plug in 2, you'll notice I get 6 minus 4, which is 2. If I plug in 3, it's 3 times 3 is 9, 9 minus 4 is 5. If I plug in 4, 3 times 4 is 12, 12 minus 4 is 8. And every single term I use is accurate for what I'm looking for. Now again, this is not the only solution that would have worked for this example. I could have started at 1 or 0, and that would have changed this entire formula, but it would still come out to be the exact same summation, even if it's not the same sigma notation. In this last example right here, all we need to recognize is that this is 2, 4, 6, and I'm assuming it's going to be 8, and so on and so forth. We are simply adding 2 to the variable in front every single time. So that means that my summation is going to start off at I equals, I'm going to go ahead and do 1, and it looks like because I'm going to go from 3 to 31, I'm going to go from 2 to 30. Looks like I'm going to have at least 15 terms. Again, 2 times 2 is 4, times 2 is so on and so forth. So it looks like I'm going to go ahead and deal with, first off, my numerical value. Then you'll notice that x in every single one of these examples doesn't change. So x is going to be a constant in this summation, in theory. Then you'll also notice that it goes 3, 5, 7, and these are all odd terms. That it's very similar to the previous example over here where I started with 3. And if I started with 3 such that n started with 1 or I started with 1, that means I'm working with the 2n plus 1 case. So my power is going to be 2n plus 1. Now let's verify that these powers work, and you'll notice if I go I equals 1, I plug in 1, I get back a power of 3. Perfect. If I want the last term, and again I thought it was 15. If I use 15 for my example, and I plug 15 in here, that's actually going to give me 31. So that does work for the last value. Again, just to be safe, if I plug in 2, I do get 5. That's the second term. Now, how do I get this example right here, this piece, the 2, the 4, the 6, and so on and so forth? Well, I want 2. Sorry, this should be I, this should be I. 2 times just I. Because again, if I plug in 1, I get 2. If I plug in 2, I get 4. If I plug in 3, the next value, I get 6. If I plug in 15, I do get 30. So that is my summation for this example. And again, notice, in some cases I might use I. In some cases I might use n. You just have to be very careful with what the index variable happens to be and stick with that index variable.